C# and AI Masterclass by Edgar Milvis Volume 8, Chapter 9. Now, let's talk about Chapter 9, Prompt Engineering Techniques in C#, Few-shot, CoT. Now, let's explore theoretical foundations. The theoretical foundation of prompt engineering within the Microsoft Semantic Kernel rests on a fundamental shift in perspective. We are no longer merely calling an AI model, we are orchestrating a computational process. In earlier chapters, specifically when discussing Book 7, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns, we established the architecture of the kernel itself, the dependency injection, the connector patterns, and the basic function calling. However, raw model access is insufficient for deterministic, reliable enterprise applications. To bridge the gap between probabilistic language models and deterministic software logic, we must apply rigorous prompt engineering techniques directly within the C# type system. This subsection focuses on the theoretical foundations of few-shot prompting and chain of thought, CoT, reasoning. These are not mere text-wrangling tricks, they are mechanisms to manipulate the attention and inference pathways of the underlying large language model, LLM, by leveraging the structural advantages of the C# language. Moving on to the nature of probabilistic inference versus deterministic logic. To understand why prompt engineering is necessary, we must first visualize the LLM not as a database, but as a high-dimensional probability distribution. When you send a raw query to a model, you are effectively asking it to complete a pattern based on its training data. Without guidance, the model relies on the most statistically likely completion, which is often generic, shallow, or hallucinated. In C# engineering, we are accustomed to strict contracts. We define interfaces, classes, and methods with explicit types. The compiler enforces these contracts. An LLM has no compiler, it has a context window. The prompt engineering techniques discussed here serve as the compiler for the AI, enforcing structure and logic before the request ever leaves the application. Now, let's explore few-shot prompting, the show, don't tell paradigm. Few-shot prompting is the technique of providing the model with a set of input-output examples within the prompt itself before asking it to perform a task on new data. In the context of C# and semantic kernel, this moves beyond simple string concatenation. Turning our attention to theoretical foundations. In a zero-shot scenario, asking the model to perform a task without examples, the model must infer the user's intent from the instruction alone. This is prone to ambiguity. For instance, if we ask a model to extract entities, it might return a list of names, dates, or a summary, depending on its training bias. Few-shot prompting works by establishing a local context within the prompt. It essentially performs meta-learning at inference time. By providing examples, we are narrowing the model's search space. We are forcing the model to recognize a pattern and replicate it. In C#, we can formalize this using the strategy pattern or the template method pattern. We don't just hard-code strings. We define a structure where examples are first-class citizens. Consider the analogy of teaching a new junior developer. If you simply hand them a spec sheet that says, write clean code, the result is unpredictable. If you hand them a spec sheet and 3 code reviews of previous PRs showing exactly what clean code means in your repository, variable naming, structure, error handling, their output will align with your expectations. Few-shot prompting is that code review embedded directly into the execution context. Let's discuss architectural implications in C#. In semantic kernel, we treat few-shot examples as data. We encapsulate them in classes. This allows us to swap out example sets dynamically based on the user's context or the specific domain, e.g., medical versus legal extraction, without changing the underlying model call. This relies heavily on records, introduced in C# 9, and immutable collections. Because prompts are often cached or logged, immutability ensures that the examples provided to the model cannot be accidentally mutated during the orchestration pipeline. At line 1, we import system, collections, immutable. This is a crucial architectural decision. We are opting for immutable collections, which inherently offer thread safety and predictability. In a highly concurrent environment, like an AI service processing multiple requests, mutable collections could lead to race conditions and unexpected behavior. By using immutable types, we guarantee that once an object is created, its state cannot change, simplifying concurrency management and reducing the cognitive load for developers. This choice prevents subtle bugs that are notoriously difficult to debug in multi-threaded applications. Here, we define our namespace AI, engineering, core, prompts. This helps organize our code base, preventing naming collisions and making our code more modular. Within this namespace, at line 7, we declare a record called few-shot example. Records are a C number 9 feature designed for immutable data models. They automatically generate value-based equality and deconstruction, which is incredibly useful for DTOs, data transfer objects. Notice the comment at line 5 to 6, it explicitly states that records ensure thread safety for data transfer objects. This is fundamental for robust AI applications where prompt examples might be shared across multiple concurrent requests to the language model. We define the entity extraction prompt class at line 9, which encapsulates the logic for constructing a prompt specifically for entity extraction. At line 11, we declare task description as a public string with an init accessor. The init keyword is another C9 feature that allows properties to be set only during object initialization. This enforces immutability for the task description after the object has been constructed, aligning with our overall strategy of creating predictable and stable prompt structures. We initialize it with a default value, making it convenient to use while still allowing customization if needed. Observe lines 13 to 15. We declare examples as an immutable list few-shot example. This is a very deliberate choice. Instead of a standard list T, which is mutable, immutable list guarantees that once we add examples, the collection itself cannot be modified. This is vital for few-shot prompting, as the integrity of the examples is paramount. If the examples were mutable, another part of the application could inadvertently alter them, leading to inconsistent model behavior or incorrect responses. By using immutable list, we ensure that the prompt construction logic always operates on the exact set of examples it was initialized with, enhancing reliability and debugging. At line 18, we introduce the build prompt method. This method is designed to be a pure function. This means that given the same query input, it will always produce the exact same prompt string output, without any side effects. This functional programming principle is incredibly beneficial for testing, predictability, and parallel execution. Pure functions are easier to reason about, test in isolation, and are inherently thread-safe because they don't modify any external state. The theoretical steps outlined in the comments, lines 21 to 22, show a clear, structured approach to prompt engineering, which is a critical skill in AI development. Look closely at lines 27 to 32. The comment at line 27 to 28 highlights a crucial performance consideration, using string builder or a templating engine for complex string concatenations. While the current implementation uses simple string interpolation for readability in this example, in a production system with many prompt examples or high throughput, repeated string concatenations create numerous intermediate string objects, leading to increased garbage collection pressure and degraded performance. A string builder pre-allocates memory and modifies the string in place, significantly reducing object allocations. This is a common optimization technique for performance-critical applications, especially those handling many requests per second. Now, let's explore chain of thought, CoT decomposing complexity. While few-shot provides examples, chain of thought provides reasoning steps. CoT prompting encourages the model to generate intermediate reasoning steps before arriving at a final answer. This is crucial for mathematical problems, logical deduction, and complex planning. Let's discuss theoretical foundations. The why behind CoT is rooted in the autoregressive nature of transformers. The model generates one token at a time. If we ask for a final answer immediately, the model must compress all logical reasoning into a single inference step, which often overflows its working memory, the attention window. By forcing the model to output intermediate steps, e.g., first, I need to calculate x, then I apply y, we allow the model to use its own output as context for the next token. This effectively offloads the working memory from the model's internal state to the generated text stream. Now, let's explore the grandma's recipe analogy. Zero shot, you ask, how do I make cookies? She might reply, mix flour, sugar, and eggs, then bake. This is technically correct but useless for a beginner. Chain of thought, you ask, walk me through the process step by step. She says, first, preheat the oven to 350. While that heats, cream the butter and sugar. Then, add the eggs one at a time. Now you have a logical flow where step A sets up step B. In software terms, CoT is the equivalent of breaking a complex LNQ query into multiple intermediate variables or using the let keyword in a query expression. It makes the execution traceable and debuggable. Now, let's talk about C# implementation strategy, the planner pattern. In Semantic Kernel, we don't just ask the model to think step by step in a raw string. We structure the prompt to enforce a specific output format that represents the chain of thought. We often use JSON schema or XML to structure these thoughts, which C# can then parse strongly. We can utilize C# source generators to dynamically create prompts that enforce CoT. By analyzing a method's parameters and return type, a source generator could theoretically inject CoT instructions into the prompt template at compile time. However, a more common runtime approach involves the function calling capabilities of the kernel, introduced in Book 7. Instead of asking the model to output text that describes reasoning, we ask the model to invoke a sequence of native C# functions. Each function invocation represents a step in the chain of thought. Let's discuss unifying concepts, plugins as reusable prompt structures. The ultimate goal of this chapter is to move these techniques out of ad hoc strings and into reusable C# plugins. This is where the architecture of the application solidifies. In previous chapters, we discussed kernel functions. We can now define a kernel function that encapsulates a CoT prompt or a few-shot prompt. This creates a prompt as code paradigm. Let's discuss the interface analogy. Just as an IEnumerable T allows you to swap between an array and a list without changing the consuming code, a prompt plugin allows you to swap the underlying reasoning strategy, few-shot versus zero-shot versus CoT, or even the model provider, OpenAI versus Azure OpenAI versus Local Llama, without changing the agentic logic. When we define a plugin in C#, we are essentially creating a wrapper around the LLM's inference engine. The C# method signature acts as the strict interface contract. Here, we're importing essential namespaces. Microsoft.Semantic Kernel is the core library that provides the building blocks for creating AI applications with Semantic Kernel. Think of it as our toolkit for interacting with large language models, LLMs, and orchestrating AI components. System.ComponentModel is used for attributes like description, which are vital for how Semantic Kernel understands and uses our functions. Without these imports, our code wouldn't recognize key types and attributes required for plugin development. We define our namespace AI, engineering, core, plugins and declare a public class reasoning plugin. Namespaces help organize our code, prevent naming conflicts, and improve readability, especially in larger projects. The reasoning plugin class will encapsulate a set of related functionalities that an AI agent can invoke, specifically those related to logical reasoning. This block introduces the reasoning plugin class. The comments here are particularly insightful, highlighting the role of the description attribute. We're setting up a method that the AI itself will be able to see and understand its purpose. This is a fundamental concept in agentic AI, giving the LLM the ability to choose and execute tools based on its understanding of their descriptions. Without a clear and descriptive description, the LLM wouldn't know when or why to call solve with CoT async. Notice that the description solves a complex logical problem by breaking it down into intermediate steps. Attribute. This is not just for human readability, it's the contract between our code and the LLM. The LLM will read this string and use it to decide if solve with CoT async is the right tool to use for a given user prompt. The kernel function attribute marks this method as callable by the semantic kernel. It's how Semantic Kernel discovers and registers this C# method as an AI function. We also define the method signature, solve with CoT async, which takes a kernel instance and a problem string as arguments. The kernel instance is crucial because it allows this plugin to make further calls to the LLM or other plugins, enabling complex orchestration. Here, we define the parameters for our solve with CoT async method. The kernel parameter is exceptionally important. It represents the semantic kernel orchestrator itself, allowing this plugin to recursively call other plugins or even the LLM directly. This is how we build complex, multi-step AI workflows. The problem parameter, also adorned with a description attribute, tells the LLM what kind of input this function expects. This clarity is paramount for the LLM to correctly map user input to function arguments. This section outlines the theoretical steps for a chain of thought, CoT, implementation. CoT is a powerful prompting technique where the LLM is encouraged to think step by step before arriving at a final answer. This dramatically improves the accuracy and reliability of LLM outputs for complex reasoning tasks. The steps listed here, constructing a prompt, sending to kernel, parsing, returning, are a blueprint for how a real-world CoT plugin would operate, involving multiple interactions with the LLM to generate and refine reasoning. This block clarifies that the current implementation is a placeholder. Return await task.from result, simulated CoT result, means we're returning a predefined string immediately. In a production scenario, this line would be replaced by actual logic. This logic would likely involve crafting a sophisticated prompt that instructs the LLM to perform chain-of-thought reasoning, sending that prompt to the kernel instance, which we received as a parameter, and then potentially parsing the LLM's multi-step response to extract the final answer. This simulation is useful for initial testing and understanding the plugin's interface before diving into the complex LLM interaction logic. This diagram illustrates a C# application orchestrating a pipeline where user input is transformed into a structured prompt, sent to an AI model, and the resulting output is parsed back into types. Turning our attention to edge cases and architectural considerations. Token limits and context compression, few-shot examples consume tokens. If you provide too many examples, you may exceed the model's context window. In C#, we must implement logic to dynamically select the most relevant examples, perhaps using vector search, as discussed in previous books on RAG, rather than blindly appending all examples. 2. CoT hallucination. CoT allows the model to ramble. If the intermediate steps are wrong, the final answer will be wrong. In a C# agentic pattern, we should implement validation middleware. This middleware would parse the CoT steps and, using a smaller/faster model or heuristic checks, verify the logical consistency of each step before proceeding. 3. Type safety. The output of an LLM performing CoT is often verbose text. We rely on C# system, text, JSON or custom parsers to extract the final answer. If the model deviates from the expected output format, e.g., it forgets to wrap the answer in JSON tags, the application must have fallback logic. This is where resilience patterns, like Poly, integrate with prompt engineering. Now, let's explore conclusion. The theoretical foundation of prompt engineering in C# is the application of software engineering principles, encapsulation, immutability, and interface design, to the inherently non-deterministic world of LLMs. By using few-shot prompting, we provide the model with explicit examples, narrowing its search space to match our domain. By using chain of thought, we decompose complex problems into manageable steps, leveraging the autoregressive nature of transformers. Finally, by encapsulating these techniques within semantic kernel plugins, we create reusable, maintainable, and robust AI capabilities that integrate seamlessly with the rest of the .NET ecosystem. Moving on to basic code example. Here is a simple, self-contained Hello World level code example demonstrating few-shot prompting using Microsoft Semantic Kernel in C#. Now, let's explore the problem, automated customer support categorization. Imagine you are building an automated support system for a tech company. You need to route incoming user tickets to the correct department, e.g., billing, technical support, general inquiry. A standard keyword search is often too rigid and misses context. Instead, we will use few-shot prompting to provide the AI with explicit examples of how to classify text, ensuring it learns the pattern before making a prediction. Now, let's explore code example. This example uses the Semantic Kernel SDK. Ensure you have the Microsoft.Semantic Kernel NuGet package installed. Here, we're importing essential namespaces for our application. Notice Microsoft.Semantic Kernel, line 1, which is the core library providing the foundational components for building AI applications with Semantic Kernel. Microsoft.SemanticKernel.Chat completion, line 2, specifically gives us access to tools for interacting with chat-based large language models, LLMs. We also bring in System for basic functionalities like console and system, threading, tasks for asynchronous programming, which is crucial when dealing with potentially long-running API calls to LLMs. At line 8, we define our main method as async task. This is a critical architectural choice because interactions with LLMs are inherently asynchronous operations, involving network calls and potentially long processing times. By using async/await, we ensure that our application remains responsive and doesn't block the main thread while waiting for the LLM's response. On lines 13 to 16, we initialize the kernel. This is the central orchestrator in Semantic Kernel. We're configuring it to use an OpenAI-compatible chat completion service. Notice model ID, GPT-40 mini, line 14, this specifies which particular LLM model we want to use. The API key, fake API key for demo, line 15, is a placeholder. In a real-world scenario, you would replace this with a secure API key, perhaps loaded from environment variables or a secret management system, to authenticate your requests with the LLM provider. Starting at line 18, we begin constructing our few-shot prompt. This is a powerful technique in prompt engineering. Instead of just giving the model instructions, we provide it with a few examples, the shots, of input-output pairs. This guides the model much more effectively than instructions alone, showing it the desired format and behavior. The few-shot prompt string contains the high-level instruction, "You are a helpful assistant that categorizes support tickets," line 22. This sets the persona and primary task for the LLM. We also explicitly define the allowed categories, billing, technical support, general inquiry, lines 23 to 24. This constrains the model's output, preventing it from inventing categories and ensuring consistency, which is vital for downstream automation or reporting. Here, from lines 27 to 38, we provide the actual few-shot examples. These examples are the core of this prompt engineering strategy. Each example consists of a ticket and its corresponding category. For instance, I can't log into my account maps to technical support, lines 28 to 29, and where is my invoice for last month, maps to billing, lines 31 to 32. The purpose of these examples is to implicitly teach the model the patterns and reasoning for categorization without needing to explicitly program complex rules. The model learns from these examples how to generalize to new, unseen tickets. This approach is particularly effective because LLMs excel at pattern recognition and analogical reasoning. At lines 39 to 42, we complete our few-shot prompt. We introduce the placeholder, $input. This is a semantic kernel convention indicating where the actual user input, the new support ticket, will be injected into the prompt before it's sent to the LLM. By placing it after the examples, we ensure that the model processes all the guiding examples first, then applies that learned pattern to the new input. The final category, line 41, is crucial. It explicitly tells the model that we are expecting a category as its next output, reinforcing the desired response format and making it more likely to produce a clean, parsable answer. From lines 44 to 50, we create an instance of chat completion agent. This is a higher-level abstraction provided by Semantic Kernel that simplifies interaction with chat models. Instead of directly calling the chat completion service, we encapsulate the model, the instructions, our few-shot prompt, and any other configurations within this agent. This promotes modularity and reusability. Notice how we pass our kernel and the few-shot prompt as instructions. The agent will take these instructions, combine them with the user's input, and formulate the complete prompt to send to the underlying LLM service. This design pattern makes it easier to manage complex prompting strategies and agent behaviors. Here, on lines 52 to 58, we simulate the execution phase. We define a user ticket string, which represents a new, unseen support ticket that our agent needs to categorize. This is our test case. We then use console.writeLine to display the input ticket and indicate that the processing is about to begin. This provides clear feedback to the user or developer about what's happening. The chat history object, mentioned in the comment, is a powerful feature for multi-turn conversations, but in this specific example, since it's a single classification task, its full capabilities aren't being leveraged. However, using it for even single turns sets a good pattern for future expansion into more complex conversational flows. At line 60, we invoke our agent with the user ticket. This is where the magic happens. The agent takes the user ticket, combines it with the few-shot prompt, which includes the examples and instructions, and sends this complete prompt to the configured LLM, in our case, GPT-4o Mini. The await keyword is essential here, as the invokeasync method performs an asynchronous network call to the LLM service. Finally, on line 65, we print the predicted category. We access response content to get the raw text output from the LLM. The expectation, based on our few-shot examples, is that the model will correctly identify "my internet connection keeps dropping" as technical support, demonstrating the effectiveness of our prompt engineering strategy. Kernel.CreateBuilder, this initializes the Semantic Kernel Builder pattern. It is the entry point for configuring dependencies, services, and plugins. Even for a simple example, the kernel acts as the orchestrator. 2. Add OpenAI chat completion. This registers the iChat completion service into the kernel's service collection. In a production environment, you would likely use add Azure OpenAI chat completion for enterprise-grade security and scalability. For this demo, we mock the API key. 3. String few-shot prompt, raw string literal. We use C#11 plus raw string literals to define the prompt cleanly without escaping quotes. Role definition, you are a helpful assistant. Sets the system behavior. Constraints, we explicitly list the allowed categories. This is a form of constrained decoding via prompt engineering. The shots, the block labeled examples, contains pairs of inputs and expected outputs. This is the core of few-shot learning. The model analyzes these to infer the logic, e.g., login, technical support. $input, this is a template variable. In a real semantic kernel plugin, this would be bound to a function parameter. Here, we simulate the injection of the user's specific ticket. 4. New chat completion agent, we instantiate an agent. The chat completion agent is a specialized class in semantic kernel designed to wrap an iChat completion service. We pass the instructions, our few-shot prompt, and the configured kernel. This decouples the logic from the underlying model implementation. 5. Agent.invokeasync, user ticket. This triggers the AI model. The kernel combines the instructions with the user input, sends it to the configured LLM, and waits for the token stream to complete. The model processes the few-shot examples, recognizes the semantic similarity between internet connection keeps dropping and the previous technical examples, and outputs the category. Now, let's talk about common pitfalls. 1. hallucination due to ambiguous examples. If your few-shot examples are contradictory or vague, the model will produce inconsistent results. For instance, if one example maps login to technical support and another maps login to billing, perhaps regarding a login fee, the model will struggle. Always ensure your examples are consistent and representative of the complexity you expect in production data. 2. Token limit overflows. Few-shot prompting increases the prompt length. LLMs have a finite context window, e.g., 8K, 32K, or 128K tokens. If you provide too many examples, e.g., 50 shots, you may exceed the token limit, causing the model to truncate the earliest examples or fail entirely. For large-scale systems, use fine-tuning instead of few-shot prompting. 3. Hard-coded prompts versus Semantic Kernel plugins. In the example above, we hard-coded the prompt string. In a real agentic architecture, you should wrap this logic in a kernel function. This allows the prompt to be version-controlled, tested, and reused across different agents or workflows. Hard coding makes refactoring difficult and breaks the modularity of the AI system. Now, let's talk about visualizing the flow. The diagram illustrates the semantic kernel's modular flow, where a planner dynamically selects and chains plugins to process user input, contrasting the rigidity of a hard-coded approach. By scanning this code, you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. Thank you for your attention. This lesson is excerpted from Volume 8, Chapter 9 of the C# and AI Masterclass ebook series and from the volume, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns. You can find all the details here, https://github.com/edgarmillvus/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.